Hi everyone, this is the second video on radioactivity. We're looking at the different types of radioactive decay, the alpha, the beta, the gamma. What are they and how do they behave? So what we'll be looking at is exactly what they are, what they consist of. We talked about ionizing power in the last, or rather ionization in the last video. And so I did mention that these three types, these alpha, these beta, and these gamma rays can cause ionization. That's how we detect them. And it's also why they're so useful, potentially, and why they're so dangerous, potentially. So this ionizing power, how they can strip electrons from materials. And as a result of that, we'll also see how they can penetrate different materials, how far they can travel, and yeah, why. And then finally, we'll look at a small topic which isn't covered in all boards, so do check that, but whether they're deflected by magnetic or electric fields. It's just a very small topic, which I'll add on at the end. So what we should be aware of is that some nuclei um, of isotopes are unstable. Okay, I mentioned that sometimes they are too large. They want to become more stable. Sometimes they have too many neutrons, and so they need to somehow reduce those numbers of neutrons, or they need to get smaller. And when they, in order to do that, they decay and they give out types of radiation, which causes ionization. And that phenomenon is called radioactivity. So it's discovered by this guy, Henri Becquerel, discovered in 1896. Now, the process by which it happens, two important things which we'll talk about probably in a couple of videos actually, but it's important just to point this out. When you have a nucleus, so imagine here's a little nucleus. Let's redraw that so it doesn't disappear. If I have a little nucleus and imagine it's going to give off some form of radiation, okay, I might have lots of different nuclei, might have thousands, billions probably, of individual nuclei. Which one is going to decay is random. You do not know which one's going to decay. Next, you know that it's going to happen at some point, but you don't know which one. It's like having 1,000 dice. You don't know which dice, if you roll them all, you wouldn't know which dice is going to roll a six, but you know that eventually, if you kept rolling them, they would all roll a six, but you don't know which one or um, when it's going to happen. The other thing to be aware of is that radioactivity is spontaneous. That means that it's not going to be affected by external factors. It means it's not, if you heated it up, it wouldn't happen quicker. Like in chemistry, you might imagine a chemical reaction is going to happen quicker if you heat it up or if you pressurize it. With radioactivity, it's not affected by anything like that. It's very much a mind unto its own. We can't really affect what's going on. That can have benefits and drawbacks. And importantly, if you haven't got that already, I've mentioned them a few times, there are three main types of radioactivity that you need to know about. Alpha, beta, and gamma, and the first here is alpha. So I'm going to briefly describe what each of those forms are, which each of these forms are. Then we'll look at it in more detail. Okay, so I'm just going to give an overview, and then we'll look in more detail. So alpha particles consist of two protons plus two neutrons. Some of you might realize already, if I've got two protons and two neutrons, here's my two protons, here's my two neutrons, I don't have any electrons, but I could imagine that that is basically a helium nucleus. Okay, if you look on your periodic table, almost definitely what your periodic table will say is that helium is helium-4, meaning that it has two protons and a mass number of 4. So it has, remember, its mass number is the number of protons and the number of neutrons. So its number of neutrons is going to be 2 neutrons plus 2 protons. So this alpha particle is actually a helium nucleus. It hasn't got any electrons, but it is effectively a helium nucleus. 2 protons and 2 neutrons. They're generally emitted by isotopes which are very, very large, things like uranium. Yeah, uranium-235, a lot of people have heard of that. That is an isotope. It's a large isotope. It's got lots of protons, lots of neutrons. Effectively, it wants to get smaller. Okay, it's unstable. It's too big. and therefore it wants to lose some of those protons and some of those neutrons. And so it will literally just throw them out. As I say, we'll look at that in more detail in the next video about exactly what happens there. But certainly it wants to get rid of some of those neutrons and some of those protons. So here's your large nucleus, literally throwing out those protons and neutrons, throwing out that alpha particle. As a result, the nucleus is going to change, yeah? It's going to change the number of protons. So it's actually going to change the elements. You actually have alchemy going on here. If the number of protons is changing, the element is changing. Okay, the next one, beta decay. Beta decay is a little bit more mysterious and a bit more confusing generally. A beta particle is a high-speed electron. But when we're talking about nuclear decay, we're talking about the nucleus, yeah? And you should be aware that there are no electrons in the nucleus. So how is it happening that a high-speed electron is firing out of a nucleus? Well, it is mysterious and it is confusing. But what's going to happen is that actually a neutron will turn into an electron. It tends to happen in isotopes where there are too many neutrons, okay? Way more neutrons than protons. Again, that leads to instability, and somehow that isotope wants to get rid of some neutrons. But rather than throwing those neutrons out, it changes that neutron into an electron and a proton. So one of these neutrons decays into a proton and an electron. The proton remains in the nucleus, but the electron is emitted as a beta particle. So we'll see here, one of these neutrons has changed into a proton. So again, the proton number is going to go up. We have changed the element. But as a result of that change, we also get an electron produced, and that is the beta particle. So this electron, this beta particle, it is an electron, but it has not come from the outside of the nucleus. It hasn't come from the orbit of the nucleus. It's come from the nucleus itself, even though there were no electrons in the nucleus. So that's why it can be confusing. Finally, probably the easiest is gamma radiation. With gamma radiation, there is no change in the nucleus at all, but it still comes from the nucleus. It tends to happen when either beta or gamma radiation have occurred as well. And as an extra result of that as an extra result of that beta or that alpha decay, there is some extra energy built up within the nucleus. And the nucleus just wants to get rid of that extra energy. It's probably the easiest way to think of it. And as a result, that extra energy is given off as a gamma ray. Now, gamma ray, you will be aware from electromagnetic spectrum, your work on waves, that gamma radiation is a form of the electromagnetic spectrum. Electromagnetic waves are forms of energy. Yeah, so it's literally just a form of energy with a very, if you can remember, high frequency. Okay, like very close, very similar to X-rays. But in fact, the only real difference between gamma rays and X-rays is that gamma rays come from the nucleus, whereas X-rays come from the electrons outside the nucleus. But they are pretty much the same thing. You can't actually tell the difference between gamma rays and X-rays. In gamma decay, the gamma ray is emitted, the nucleus loses energy, but there is no change to the number of protons and neutrons. You can see here that these two nuclei are exactly the same. And so there is no change in the nucleus. We'll look at how that affects anything in the next video, but to all intents and purposes, this is going to stay exactly the same, not only the same element, but also the same isotope. There are no changes to the nucleus, just loses a bit of energy. So a little recap, to see if you can fill in these gaps. Here's an unstable nucleus. It's going to decay into a new nucleus, and in doing so, it's giving out an alpha particle. See if you can fill in the gaps there. Give you a second. So alpha an atom decays into a new atom and emits an alpha particle, 2 protons and 2 neutrons. Kind of came out of my mouth without even thinking about it. 2 neutrons. Remember what that is the same as, 2 protons and 2 neutrons. Sometimes it's considered the same as the nucleus of a helium atom. Helium atom without the electron, i.e. the nucleus. That is what happens in alpha decay. How about the next one? Again, you've got an unstable atom, probably with too many neutrons, if you remember. This time it's going to change into another new nucleus, different numbers of protons, different numbers of neutrons, so a different element altogether. And an electron or a beta particle comes from that nucleus. How does it happen? See if you can fill those in. So this time it says beta, an atom decays into a new atom by changing a neutron into a proton. Yeah, the neutral neutron turns into a positive proton and a negative electron. The fast-moving high-energy electron is called a beta particle. And the final one, this time we've got an unstable nucleus as always, and it's turning into a new nucleus, and therefore it's producing another form of radiation. So in this case, it's giving out alpha decay. It might be giving out beta decay, but in this particular diagram, it's giving out an alpha decay. But in doing so, it's also got unstable energy. And so it additionally gives out some gamma radiation. What is that gamma radiation? Have a quick go at that. So the answer is gamma after alpha or beta decay, surplus energy is sometimes emitted. This is called gamma radiation and has a very high frequency with short wavelength. Yeah, it's just a form of electromagnetic spectrum with a short wavelength and a high frequency. The atom itself is not changed. So this atom gives out its alpha decay. Then beyond that, it does not change. The gamma radiation does not change. I'm not massively keen on this diagram because it looks like the particle has changed. But by emitting the actual gamma radiation, it does not affect the nucleus at all. So we've got alpha, we've got beta, we've got gamma radiation. We want to know what they do. How do they affect things? So just another recap. An alpha particle consists of 2 protons and 2 neutrons. Hopefully you're bored of me saying that because you know it, ingrained in your brains. Now here's why it's important. It is strongly ionizing. Now, what does that mean? We talked about ionization in the first video in radioactivity. It means that an electron is stripped or added to an atom. And let me explain, actually, let's look at these other things first. So a beta particle is a high-speed electron, we should know that. And it's produced when a neutron decays into an electron and a proton. This one is moderately ionizing. Okay, so it's going to strip or it's going to add electrons, but not as much as alpha particles. I'll talk about exactly how this happens in a second. Gamma radiation, very high frequency electromagnetic waves produced when an unstable nucleus loses energy, and these are weakly ionizing. Now let me explain what's actually happening here. So if I have an atom, okay, and here's my nucleus with my protons and my neutrons, and here's an electron, and here's an electron. If I imagine that I've got a big, chunky, relatively big, chunky alpha particle, 2 protons and 2 neutrons. In fact, let's put a few more electrons in here. Let's imagine there's 1, 2, 3, 4, 5 electrons here. And we've got this alpha particle here. What's going to happen is this alpha particle is going to approach that atom, and if it's going to ionize it, it's going to literally kick out one of those electrons. So with that in mind, I want you just to think about why would it be that alpha particles are strongly ionizing? Why would it be that beta particles are moderately ionizing? And why would it be that gamma radiation is weakly ionizing? Think about the process I've just described. Think about the nature of alpha, beta, and gamma particles or radiation, and why might they be strong or weakly ionizing? Just have a little think. Okay, so let me explain hopefully a little bit more. So if we look at this diagram again, my very skewy diagram here, think about our alpha particle. It's relatively very large, yeah? It's much larger than our tiny little electron that is flying along. Think back to video 1, the electrons are tiny, whereas this has a relative mass of 4. So it's very big. It's also very charged. Yeah, it's got a charge of 2 plus. It's got 2 protons and 2 neutrons. So overall, it's very charged. Now, if you imagine that these tiny little electrons on whatever atom this is being approached by this big, hefty, massive sort of, it's like, imagine these electrons are little ping pong balls being approached by a chunky football. It's going to kick out those electrons really easy. It's going to kick out those ping pong balls really easily. So just by dint of its huge mass, relatively huge mass, those electrons are going to get kicked out very easily. Even if it didn't hit the atom directly on, it's also highly charged. So imagine it goes here. Here's another alpha particle. It's highly charged. It's got a charge of 2 plus. And so what's it going to do? It's going to attract those electrons to it as well. And so there's 2 reasons why that alpha particle might be able to ionize. It's going to be massive, relatively large, so it's going to kick out those electrons. It's also highly charged, so it's going to attract those electrons and draw them away from the atom. Either way, it's going to help remove an electron or more than one electron from that atom. In other words, it is ionizing. If we think about the beta particle, here's my beta particle, and I'm going to think about it in similar terms, okay? Here is another atom with its 1, 2, 3, 4, 5, let's say 6 electrons. This electron, this beta particle, gets close to it. Well, it's got a slight charge, so it might kind of repel one of these electrons. It's negatively charged. These electrons are negatively charged. So it's going to have some force on it. It might repel it to the extent that it might kick out an electron, or it might somehow, I don't know, cause it to either gain or lose an electron there. But it's not very strongly charged. So the chance of that happening is not as great, certainly, as an alpha particle. It's also much less massive. Remember, it's got a relative mass of 0.005, way, way smaller than a proton or a neutron, or certainly an alpha particle. So in terms of kicking it out by brute force, it's like a ping pong ball trying to knock out a ping pong ball. It might happen, but it's not going to be as obvious as a football kicking out a ping pong. Football's going to give it a good boof, and it's going to kick out an electron. Whereas a ping pong ball trying to kick out a ping pong ball is not going to be so obvious. So it can ionize, but definitely not as strongly as an alpha particle. It is moderately ionizing. Our final one, again, here's our atom with 1, 2, 3, 4, 5, let's give it a 6th electrons. This time, we've got a wave. That wave has a lot of energy, but it has no mass at all. Okay, it's literally like light. It's like shining a torch on something. It's got lots of energy, but no mass and no charge. So because of its energy, it can, if it hits exactly bang on, it can knock an electron out, but with no mass and no charge, it's not going to have the same force, and it's not going to have the same attractive or repulsive powers as either beta or gamma, and therefore it's going to be weakly ionizing. So to summarize that, get rid of my brilliant pictures there. Why is alpha particle so ionizing? It has a large mass, a large charge, and therefore it's more likely to kick out an electron. Gamma at the other end has zero mass, zero charge, has a lot of energy, but it's less likely to remove an electron, so it is weakly ionizing. And beta is somewhere in the middle. Yeah, low mass, but medium charge, therefore moderately likely to remove an electron and cause ionization. Now, you definitely need to know that alpha is highly ionizing, beta is moderately ionizing, and gamma is weakly ionizing. Sometimes the higher level questions will ask you why that's the case. I personally think it's really helpful to add to your understanding as to why that's the case. The questions aren't that common, but if you want some higher level questions, or if you're given some high level questions, I think an understanding of that is really helpful. Okay, the next thing to look at is the penetrating power of these alpha, beta, and gamma radiation. Again, I want you to think about why what I'm about to describe is happening. First of all, you do need to know this off by heart, okay? Just as a matter of fact, you need to know that alpha particles can pass through, okay? They will literally just shoot straight through, like a bullet would pass straight through a few centimeters of air or paper. So paper is going to stop alpha particles. But beta would pass straight through paper, and gamma would pass straight through paper, as I said, just like a bullet. But the alpha, maybe like my ping pong ball again, gets stopped by a piece of paper. Beta can go a bit further. Okay, it can go through that paper, can go through a few centimeters of air, but it will get stopped by a centimeter of aluminium or about a meter of air. Then it will get stopped. Okay, so it won't penetrate through those things. Whereas gamma will. Gamma is much more penetrating. It can go through the paper, it can go through the meters of air, it can go through the aluminium, centimeter or so of aluminium, but it will get stopped by several centimeters of lead or 1 meter of concrete. So obviously gamma, if we want to stop gamma penetrating things, we need to use much more shielding. Alpha is generally stopped very, very easily. Question is again, why? Why would that be the case? And to answer that, you need to think about the ionizing features again. So if we go back, here's a little summary of what we've got. Now, if I imagine, I'm going to just give the example of alpha, okay, because it's the most sort of obvious one to explain. If I imagine that there is air here, okay, there's lots of oxygen and nitrogen atoms, okay, and I'm going to draw in an alpha particle approaching. Here's my alpha particle approaching. Remember, it's 2 protons and 2 neutrons, but I'm just going to draw it as a red dot. Now let's imagine that this alpha particle is approaching an air particle here. And because it's so strongly ionizing even though it's not hitting bang on, it's going to ionize that maybe oxygen atom. In doing so, it's interacted with that oxygen atom and it has ionized it, and it's going to lose a little bit of energy. So it's going to plow on. It's not now going so fast. It's lost some energy by interacting with an atom. It's lost some energy. So it carries on to the next atom. Now it's got much closer. It's definitely going to ionize that one. It's interacting with that atom, so it's lost even more energy. By the time it gets to the third atom, hits it bang on again, it's going to lose lots of energy. By interacting with each of these atoms, that alpha particle is losing energy. Each time it ionizes, it is losing energy. And therefore, because it's so ionizing, it loses that energy very quickly. And so it's not going to get very far through this air. If I now compare it to, let's say, a beta particle is going to be much smaller than that. So let's just draw that again. Beta particle here, tiny little beta particle. This beta particle passes through, even though it gets quite close to this, it might just about ionize that one. Okay, so it ionizes that one, it loses a bit of energy. It gets close to this one, but it's not very ionizing, so it's not going to manage to ionize that one because it's got a small mass, a small charge. Doesn't manage to ionize that one. So it can keep going. It's only going to ionize the ones that it gets very close to. Because it's not as ionizing, it doesn't lose energy so quickly, and therefore it is going to be more penetrating. It's going to go further. Finally, if we had our gamma ray here is just going to go straight through. It doesn't interact with that one, doesn't interact with that one. It's only if it hits one bang on that it might ionize it and lose a bit of energy. But the basic gist is that because alpha is so ionizing, it loses energy very quickly as it interacts with more particles. Gamma at the other end of the spectrum, if you like, can pass through unimpeded by atoms because it's not ionizing any of them. And so it's not losing any energy. So here is your sort of summary of that. Don't forget, alpha particles are highly ionizing. Every time they interact with an atom, they ionize it and lose energy as a result. As they lose the energy, they slow down and eventually stop. So the more highly ionizing the radiation is, the less atoms it needs to stop it. And as a result, you get those patterns of penetration power or absorption. Okay, I said this was a very small topic at the end, but you just need to be aware of the fact that each of these forms of radiation can be affected by electric fields and magnetic fields in different ways. Electric fields is fairly straightforward. We know that alpha particles are positively charged, and so they are going to be attracted to a negative electrode. But they're very heavy, and so they're not going to be deflected by very much. Okay, there might be a large force on them, but you need a much larger force to deflect them by a lot. Beta particles, they are negative, so of course they are going to be deflected towards the positive. They're going to be attracted towards the positive. Why are they deflected by so much more than the alpha particles? Because, of course, they are much, much lighter. So you need a much smaller force to divert them, to affect their motion. Gamma rays are neutral, and so they are not affected by negatives or positives. They are just going to go straight through. Alpha particles and beta particles are deflected in their opposite directions due to their opposite charges. Due to their much larger mass, alpha particles are deflected far less than beta. Gamma rays are not deflected at all. And then finally, we've got our magnetic fields. Now, for reasons that you will look at when you look at electromagnetism, they are also affected, okay, in a similar way. Not literally that positives will go to norths and negatives will go to souths or anything like that, but they are interacting. The fields, magnetic fields and electric fields, interact in a way that we'll look at, as I say, when we're looking at magnetic fields, electromagnets and magnets. But all you do need to know is similar idea. The alpha particles would be deflected. Beta particles will be deflected more because their masses are much smaller. Alpha particles with gamma rays with no charge will not be deflected at all. Okay, so for now, just be aware of that fact. And later on, when I add a video on electromagnetism, that will be clearer. But just know those. Okay, so a nice little thing to fill in here, little summary for you to fill in. Have a little go at filling it in. It's a nice thing for you to have on standby as a summary. Hopefully, have a go at that, pause the video, and I will just fill this in for you now. So filling this in, alpha particle has a charge of 2 plus, beta particle 2 minus, gamma. Let me completely not mess that up. Beta is 1 minus. Thank you for those that were shouting at the screen. The mass of this, the relative mass is 1. The relative mass of this is 0. This is where I mess up, isn't it? These are alpha, beta, gamma. I'm thinking protons, neutrons. The mass of an alpha particle is 4, mass of a beta particle is negligible. And gamma again is 0. Penetrating power is low. Beta, medium. Gamma is high. The range, roughly a few centimeters of air or one piece of paper. Beta, maybe a meter of air or 0.5 centimeters of aluminium or 1 centimeter of aluminium. Gamma radiation, you can go through 10 centimeters of lead or 1 meter of concrete. What is it? Alpha particles, 2 protons and 2 neutrons. Beta is an electron, but importantly, from the nucleus. Okay, you can go into more detail. It's a neutron turning into an electron and a proton. Gamma is electromagnetic radiation. Ionizing ability is high for alpha. Beta is medium. And gamma is low. And then other info, maybe go through the video again, just see if there's any other information, maybe about the electric fields or the magnetic fields or anything else you want to add. But that's a really useful summary sheet just to have kept somewhere for you to refer to and to eventually memorize. Okie doke. So that's what we've looked at. We've looked at the 3 types of ionizing radiation, alpha, beta, gamma, which one's strongest, which one's weakest, and why. Which one's strongly penetrating and why. And then also how electric and magnetic fields might cause them to be deflected. Hopefully that all makes sense. Let me know if any problems and check out my Facebook group or book a call there if you need any help. Okay, cheers. Bye-bye.